So we've got dynamics, engineering 212. We talked about the syllabus and whatnot. We can get into the material, which is going to include some basic definitions, some basic assumptions, and then we'll start getting into to problems and so forth. The areas that we're going to look at in here. Can you see that? Okay, good. Is that right? Can you see that fine? Okay. So my eyes are so bad. I went out there and looked at it. Oh, it still looks a little fuzzy, but I think that was just my eyes. So anyway, so we're going to talk about kinematics. What's kinematics? You probably saw that in physics. Kinematics is motion without regard to cause. Okay. So if we go back and look in history, that we attribute a lot of that work to Galileo. That was about 1590. So I could put this up here. About 1590, dropping things off of leaning buildings. He was born in Pisa, of course, the Leaning Tower of Pisa and whatnot. So motion without regard to cause. What is a body's position? What is its velocity? What is its acceleration? But we don't really ask the question, what causes that acceleration? What causes that velocity? Then as we go through history, about 100 years later, we have Newton's 3 laws published in the Principiate in about 1687. So in 1687, so just almost 100 years later, Newton's work, one of his many works, is his classic 3 laws. You have the a first law that a body in moving at rest or moving in a straight line with constant velocity will remain that way unless acted on by an unbalanced force. And you can find these Newton's laws in your physics textbook, in the textbook for this class. You could Google them if you wanted to. The second law, of course, is the classic force is equal to mass times acceleration. And finally, the third one is one that we don't want to forget, the notion that there are equal and opposite reactions. You sitting there in your chair pushing down, the chair is pushing up. We don't want to forget about both of those forces. So that's kinetics. And all of a sudden we started talking about forces. We're going to talk about, well, if we apply a force to something, what acceleration do we get? Okay? So we're not just talking about motion, we're talking about what causes that motion. So it's going to take us about 3 weeks to cover about 100 years of history. We're going to spend about 3 weeks on kinematics, and then we're going to get into kinetics. Then we're going to move on to what's known as scalar solutions. We will have work and energy. We'll talk about the work-energy relationships, impulse-momentum relationships. A lot of these are path-independent, so that's why we call them scalar solutions. And that'll be about 2/3 of the class, and then we're going to start the class all over again and do this whole entire process over again, but instead of having a point, instead of thinking of a horse or a car or a boat as a point, usually at its mass center, we're going to start to think about a rigid body. Okay, and we're going to do this again for a rigid body, which has more degrees of freedom, more equations, more complexity, but it makes our models better. I mean, if we're looking at driving our car down I-5 and we're not spinning on ice maybe, thinking of it as a point is probably a pretty good model. But if we look at our car moving down I-5 and then at the same time it's turning end for end as it goes down the road, then we probably need to start thinking about it as a rigid body. So we need a more robust model. So we'll go back and we will make our model better by thinking of things not as just a single point or particle, but thinking about them as a rigid body. So that'll take most of the term. Are there questions? Make sure you're asking questions here. If I've pre-prepared some of this, so I may move a little bit fast, but remember, you're going to be able to see a PDF of this. You could fill in the blanks if you want to. I plan to post this, so I mean, I assume everyone's okay asking questions. You don't have to say your name. But if you're too shy to ask questions on the video, come by office hours. Probably I will repeat. Yeah. So I say, yeah. Your question is, will the microphone pick you up? And it's probably not that well. So I'll repeat it. Thanks. Okay. Other questions? It does pretty good, quite frankly, over to you, but you're probably not going to yell loud enough. So, other questions? Too polite. Okay, so looking at some basic concepts, we need to talk about reference frames and whatnot. Let's say that we have a train car and we have a person in a train car, and the person is walking to the north at 5 feet per second. Like I've got up there, I guess I've got it kind of moving towards the south, but take one direction, and the person is moving in that direction at 5 feet per second. And we'll say that the train car is going in that same direction at 88 feet per second. I kind of like 88 feet per second because that's actually 60 miles an hour. Okay, if you do the conversion, 60 miles an hour is 88 feet per second, which is probably worth thinking about. Now, there'll be a few times in here that I will indicate, get you to try and think about when you drive along at 60 miles an hour, you're covering a tremendous amount of ground every second. Okay. And you know, I'm not going to give you the blood runs red on the highway speech every day, but if I can get you to think about maybe being careful and driving a little more careful, that'd be a good thing in here too. 60 miles an hour, 88 feet per second is a lot of ground, especially when you're texting and doing your homework as you're driving along at 60 miles an hour. Okay? So we've got the person going the same direction as the train car. The person's going 5 feet per second. The train car is going 88 feet per second. So we ask the question, what is the person's speed, or what is the person's velocity? Well, before someone asks that question, they might ask it relative to what, right? Becomes important. What is our reference frame? What is it relative to? Okay? If we say the person's velocity relative to the train car, what would the answer be? 5 feet per second. If we ask what the person's velocity is in relation to some fixed point out here, what would we say? 93 feet per second, wouldn't we? Okay? And you'll notice that I put these double quotes on fixed because while this is up here on my cart and seems relatively fixed, it actually isn't, is it? Every so often my cart takes a trip back to my office. That's not very fixed, is it? I mean, let's say that we go up here, and one of the big things you got to do is keep me from writing on the board with a Sharpie this term. Okay? Let's say that we put a mark on the board up here, and we say that this is going to be our fixed point. Okay? Is that fixed? What's fixed to the building? Is the building fixed? That's fixed to the ground, maybe. Maybe not so much in an earthquake. But let's not say we're having an earthquake. Is the ground fixed? Well, the ground, we're actually moving through space, right? We usually don't have to worry about and think about that when we're designing things like dump trucks and cruise ships and things like that. But when we start thinking about designing, maybe shooting a missile out of the sky or something, is the Earth as a fixed point a good enough assumption for us? It isn't. We're going to have to go out into space and take some point in space and say that that's our fixed point. And when you think about the dynamics involved in shooting down an incoming missile or something like that, it's really tremendous in its nature. Well, we can make this problem quite a bit more complicated, and we will make it more complicated. Let's say that they weren't going in a line, so we had the person walking to the northeast, and we had the car going to the northwest. What's the relative velocity? That's a more difficult problem, and we're going to be talking about that in the future. If we look back to the beginning of World War II, there was a Doolittle's Raid that's been captured in a lot of different movies. Probably the best one, in my opinion, is the old black and white movie 30 Seconds Over Tokyo. And what they did is after the Japanese bombed Pearl Harbor, there was a real desire to get back at them. It was not that great of a mission from a tactical standpoint in terms of going and getting some piece of land that we needed for island hopping. It was rather just to dealt a blow, give a blow to the mainland. And what the plan was is that a gentleman by the name of Jimmy Doolittle took B-25 Mitchells, okay, and they put them on an aircraft carrier. So this is a man that put bombers on an aircraft carrier and somehow got them off of an aircraft carrier out in the middle of the Pacific because he wanted to bomb mainland Japan. Okay, so we're going to take bombers off of an aircraft carrier and bomb Tokyo. Okay. Fairly hard to get a fighter aircraft off of an aircraft carrier, let alone a bomber, right? If you look at the newsreels, Jimmy Doolittle, he was a great leader. He took off first because the first plane off is the most difficult. That they had the planes all lined up on the aircraft carrier. So had lots of planes here, all stacked up. The first one had the least amount of runway, and if you look at it, his almost dove off the front of the ship. But the thing to getting an airplane into the air is to get maximum velocity across the wings, right? So how do you do this? And when we think about relative velocity, what are we going to do? We've got a certain velocity for the airplane, don't we? So we'd have the velocity of the airplane. Then what would we do to make our odds a little better? Yeah, we'd get the ship going. We'd have the velocity of the ship, wouldn't we? Okay. And then which would we, obviously we might think, well, we want the ship pointed towards Tokyo, but that's probably not the best way to launch. What would be the best way to launch? Into the wind. Okay, so we have the velocity of the wind, don't we? So we'd say that the velocity of the wind across the wings of the airplane would be the velocity of the plane plus the velocity of the wind plus the velocity of the ship. We'd have to call down to the engine room and have them run the ship at full speed to try and get maximum velocity. Okay. So that was the gist of it. Their goal was then to crash land in China. They thought they were detected about 900 miles early, so they had to take off early. A lot of them ran out of fuel, so the mission did not go as well, although they did a great job of bombing Tokyo. But it's a great study in relative velocity in terms of trying to maximize that wind across the wing of an aircraft. Questions with that? Well, we're going to see this in a little more complex notion. I want to get you to thinking about this early because this is something students struggle with. Let's say that we have an automobile that's moving along. I just drew the back half of the automobile, or I guess the front half if the automobile is going in reverse. You can take whatever choice you want. But let's say that we have an automobile moving along at some velocity. And we look at the tire. So we'd like to investigate more what's going on with this tire. So we've got that tire. If the tire's not spinning, so we're not breaking traction, we're actually going to see that the tire has no velocity with respect to the ground. That is, this point here, the velocity is equal to 0. And then the center of the tire is attached to the axle. It's probably attached to the suspension. So it'll have the velocity of the car. And the top of the tire, we'll see, will actually have twice the velocity. So this is a hard thing for people to wrap their head around. I mean, up till now, when we were talking about the train and Doolittle and whatnot, that all made sense. But this one's probably quite a bit more difficult. Okay, so your assignment over the next few weeks, besides doing your homework, is to find a tracked vehicle, because you can really see this very easily on a tracked vehicle. So a Caterpillar or a track hoe, or I guess a tank, depending on where you live and whatnot. But the vehicle will have some velocity, and you'll notice that the bottom of the track, the velocity is equal to 0. I mean, it puts down the grouser, it is fixed with respect to the earth, and if you look at it then, the top of the track is moving at twice the velocity. It's quite obvious to see with a tracked vehicle. So that's your assignment over the next few weeks before we get to this subject, is to look at that. But this is really the notion of relative velocity. This tire has 0, the bottom of the tire has 0 velocity with respect to the ground. The middle of the tire has the same velocity as the car, and the top of the tire has twice the velocity of the car. So, questions with that? So we're going to spend a lot of time going and looking at relative velocities. So that's kind of your homework. We'll spend a lot more time talking about this in the future. Well, to get started with our work then, I'd like to, like I said, we're going to spend about 3 weeks in kinematics. So particle kinematics. Did you use the variable s for displacement in physics? Okay, great. So let's say that I've got some body here, and at some point in time it's located right there, and sometime later it's located at a different point. So at t it's located here, and at t plus delta t it's located there. I can say the distance that it's traveled is s, so I talk about the displacement delta s. And I can say then that the velocity, by definition, is the change in position divided by the change in time, or that the velocity is equal to delta S over delta T. That gives us the classic equation that you've probably all used, distance equals rate times time. I mean, if you've driven to school and you wonder if you're going to be on time, you've probably used that equation, right? Distance equals rate times time. If you drive 60 miles an hour, that's about a mile a minute. That makes it pretty easy to figure out how long it's going to take you to get to school. It's probably not a good plan in a residential neighborhood, but out on the highway, that makes for easy math, doesn't it? Okay. So you probably all use that, and that's really just a rearranging of velocities equal to the change in position over the change in time. Well, also by definition, we can go on and say then that acceleration is equal to the change in velocity over the change in time. So if we take these two expressions, velocity is equal to delta S over delta T, and that acceleration is equal to delta V over delta T, and we take the limit as delta T goes to 0, we come up with our equations that we will use over and over again. That velocity is equal to ds over dt, and that the acceleration is equal to dv over dt. Now, you probably saw those in physics, right? Now, these are certainly vector quantities. Usually we don't put vector hats on them because they're all read in context that they are vector quantities, but certainly with acceleration and velocity, those are vectors. This then leads us to the notion of looking at a curve for the position. So if we say that our position with respect to time is given by a curve like this, its slope is delta S over delta T. Slope is rise over run, right? Slope equals rise over run, which is going to be delta S over delta T. Well, delta S over delta T, do we have a definition for that? That's actually equal to the velocity, isn't it? So it should not surprise us that this velocity is a straight line, since that curve was, the slope of that was constant, right? So then what's dv over dt? 0. Horizontal line has a slope of 0, doesn't it? So it should not surprise us that the acceleration down here is also 0. So as you probably saw in physics, as we go from this curve to this curve, we do what? We differentiate, don't we? And as I go from this curve to this curve, I differentiate. How do I get the other way? Let's say that I have acceleration. How do I get to velocity? Integrate. Okay, that's the next math class, Math 252, isn't it? I integrate. And how do I get from velocity to position? Integrate again. Okay, and we're going to do some examples in time of that. But I think that this is probably not new stuff to you, right? You saw most of this in physics. The questions with that? Best question. I got a pen. I can make whatever figures we need. I can still draw a stickman. Yeah, it works. Okay. Okay. So this can have some velocity or whatever. Let's look at these here, particularly this one and this one. Our velocity is equal to ds over dt, and a is equal to dv dt. And we'll get to a stopping point today. Incidentally, these pages, I usually try and number them before I make a PDF of them. I'll put it in there, so this will be page 5 of 5, page 4 of 5, and so forth. So I'd come back in here. This would be 5 of 5. But so I start out with our expression that we just saw on the last page. V is equal to ds dt, and a is equal to dv dt. And I solve both of those for dt. So dt is equal to ds over v, and in this case dt is equal to v over a, solving them both for dt. Well, I kind of glossed over this step in here, but of course, I don't know that we would need to do this. Most people recognize dt is equal to dt, isn't it? So making the substitution, then I can say, therefore, that ds over v is equal to dv over a. And solving that, when I cross multiply, I come up with an old friend that's very important. V dv is equal to ADS. So probably in physics you used a lot of what's known as kinematics equation, V naught, or V is equal to V naught plus AT. Do you remember that one? What we're going to do is we're going to use these three expressions here, 1, 2, and 3, to derive those kinematics equations. But probably the most important part of that process is what we're going to have to commit to being constant in that process, and that's going to be constant acceleration. If you don't have constant acceleration, this is as good as you get. So when we get together next time for lecture, we're going to take these three expressions, these three equations, and we're going to see if we can come up with our kinematics equations. Questions with that? No? I'll see you next time.